Hello, I'm here today to present Phyloformer towards fast and accurate phylogeny estimation with self-attention networks, a preprint of which is available on bioRxiv. The problem at hand is that of phylogenetic reconstruction, namely, given a set of homologous sequences, protein sequences in our case, we want to reconstruct the tree topology which describes their evolution from a common ancestor. One issue that makes the problem hard is that the number of possible binary and rooted tree topologies grows super exponentially with the number of leaves. For instance, with 10 sequences or 10 leaves, we already have more than 1,000,000 possible tree topologies. This entails the fact that state-of-the-art methods for the task as maximum likelihood and Bayesian inference need to explore a huge tree space, which makes them computationally costly. And for the same reason, existing deep learning approaches, which frame the problem as a classification problem, are limited to trees with 4 leaves. Another class of methods works rather by computing distances between sequences. Indeed, one can see the branches of a phylogenetic tree as labeled with positive branch lengths, positive weights which represent the expected number of substitutions per site in a sequence evolving along the branch. This naturally defines a metric on the set of leaves, with the distance between two of them being given by the cumulative sum of the branch lengths on the path along the tree going from one leaf to the other. A distance-based method as neighbor joining is fast and guaranteed to recover the true tree provided the correct distances in input. But how do we compute these distances? Distance estimation is usually performed in the maximum likelihood framework, and for simple enough models of evolution, the maximum likelihood estimate of the distance between two sequences even has a closed expression. Nevertheless, the distance computation typically only considers two sequences at a time, failing to exploit all the information contained in the alignment, which reflects in worse reconstruction accuracies with respect to a full-scale maximum likelihood approach. Furthermore, these distances are not independent, as they have to satisfy, for instance, the triangle and 4 points inequalities. The idea is then to train a neural network to jointly predict all the pairwise evolutionary distances given an alignment, exploiting the context provided by all sequences. To do so, we take a supervised learning approach. We generate random trees and simulate evolution along them using a probabilistic model, thus obtaining training data consisting in alignments with the corresponding labels being all the pairwise distances in the sequences in them. That is, for an alignment with n sequences, a vector of n/2 positive real numbers. While inferring the parameters of complex models of evolution is computationally costly, sampling from them is usually cheap, so that we can generate as many data points as we need. Furthermore, as costly as the training process may be, it only needs to be done once, offering then each time fast performances for inference. Here we therefore have an overview of our method. Once properly encoded, an input alignment is processed by our neural network, which outputs n/2 positive real values, the predicted evolutionary distances, for each pair of sequences in the alignment. These can then be fed into neighbor joining to reconstruct a tree. To feed the data inside a neural network, we need a suitable representation. We can use one-hot encoding to turn an input alignment into a 3D matrix, a tensor, representing each character with a vector containing all zeros, but a 1 at the index corresponding to that character. For instance, A would become 1, 0, 0, 0, C would become 0, 1, 0, 0, and so on. Here, for ease of visualization, I've used a nucleotide alphabet, but with only 4 characters, but actually we're working with protein sequences, so our alphabet will contain 22 characters, 1 for each amino acid, 1 for an unspecified amino acid, and 1 for a gap. Subsequently, we embed each of these vector representations of amino acid into a higher dimensional space, applying to each of them the same linear transformation followed by a nonlinearity. Then we take pairwise averages over the rows to get a representation of all pairs of sequences in the alignment, representations for which we will eventually extract the corresponding predicted pairwise distances. So if in the initial representation each row corresponded to a sequence, now we have each row that corresponds to a pair of sequences. So we would have in the first row a representation of the first and second sequence, in the second a representation of the first and third, first and fourth, and so on. At some point we will have second and third, second and fourth, etc. in lexicographic order. In particular, the vector representations of a site in a pair of sequences will be those that we will be mainly working with, processing them either independently through point-wise feed-forward layers, namely applying again the same linear functions intertwined with nonlinearities to each of them, or allowing them to interact with each other through the self-attention mechanism. In the end, a final position-wise fully connected layer with a single output feature is applied to the processed representation, making it two-dimensional. Then an average over columns, that is over the sides, gives us the final prediction for all the pairwise distances. Why do we use self-attention? In a nutshell, self-attention is a mechanism which allows to update the representations of a set of objects, allowing them in a certain sense to share information among them, resulting thus in some new context-aware representations. Notably, it has been popularized in the context of natural language processing, specifically for the task of machine translation, where it allowed to encode a word inside a sentence, taking into account all the other words, as often the meaning of a word does depend on the context. In our case, these context-aware representations allow the predicted pairwise distance to take into account all the other pairs in the input alignment. Another point to put forward is that the same self-attention update can be applied to a set regardless of its cardinal, which allows us to apply our method to alignments of arbitrary size, both in terms of the number of sequences and in terms of the sequence length, the number of sites, because I didn't mention this before, but as far as we know, existing deep learning approaches not only limit themselves to alignments with 4 sequences, but also to alignments with a fixed maximum sequence length. Inside the transformer blocks, the attention mechanism is applied in 2 steps. First, over columns. For each site, information is shared among the vector representations of that site in each pair. Later, the same mechanism is applied along the other dimension, that is over rows. For each sequence pair, information is shared among the vector representations of each site in that pair. It is often desirable in the field of machine learning for a learned function to be invariant to certain transformations of the input. For instance, if we are training a neural network to recognize images of a cat, we want it to be able to do so even if we rotate the image by 90 degrees, say. One way to deal with this is to do data augmentation, that is, augmenting the training dataset with various possible transformations of the input, hoping that the neural network will learn by itself to be invariant to those. A more sophisticated way, which allows to use less training data and less parameters, is to devise the neural network architecture to be structurally invariant to those kind of transformations. In our case, we want our prediction method to be invariant to the order of the sequences in the input alignment. If we shuffle them, we want to recover the same tree. And in our case, given the devised architecture, we are guaranteed to do so. So shuffling the sequences, we still get the same predicted output tree. Furthermore, our neural network architecture is also invariant to permutations of the columns, that is, of the sites in the alignment. This allows us to exploit the assumption of common evolution models that evolution is independent and identically distributed at each site. Nevertheless, this is not a limitation if we want to deal with more complex evolution models which do model interaction between sites, because in that case we can simply use positional encoding as is commonly done with transformers in the context of natural language processing, where the order of the words inside a sentence does matter. We tested our model on two sets of simulations. The first were generated with the popular software SecGen, with which we simulated evolution according to the PAM matrix of amino acid substitution. We trained our Phyloformer model on 100,000 alignments with 20 sequences and 200 sites. Then, to test it, we generated test datasets with fixed sequence length equal to 200 and increasing number of sequences, and fixed number of sequences 30 and increasing sequence length, testing on 150 trees for each combination. We compared the performances of our method in terms of normalized Robinson full distance, a measure of the error between the true and reconstructed trees, against those of maximum likelihood, as implemented in the software IQ3, and against those of a standard distance-based method, which use neighbor joining with the maximum likelihood estimate of the distances. As you can see in the plots, we get consistently better performances than the standard distance-based method, and performances which are close to those of maximum likelihood for a setting close to the training ones, namely when the number of sequences is close to 20. We observed the same trend in several tests, including ones under model misspecification. This can be explained by the fact that as the number of leaves grows, so do the evolutionary distances between the sequences, which can then fall out of the range that the network has seen during training. The other sequence simulator we considered was previously published along with a simpler neural network, to which we can compare ours. The evolution model is a complex model employing 9 different matrices of amino acid substitution and modeling heterogeneities both across sites and along branches. 12 test datasets were generated in a previously published paper with different parameters. And we have on the left a violin plot of the mean Robinson full distance between the true and reconstructed trees for all methods and all 12 datasets. We trained Phyloformer only on the easiest parameter configuration, namely the one for which all the methods perform best, here in the upper left corner. Nevertheless, Phyloformer's distribution is always skewed towards lower Robinson full distance values, and if we look at the performances just in terms of mean Robinson full distance, we get the best performances across all methods on 9 out of the 12 datasets, being slightly outperformed in the remaining 3 only by maximum likelihood methods, which, as we shall now see, are significantly slower. We can see here on a log plot the performances of our method compared against maximum likelihood and the standard distance-based one. We see therefore that we get intermediate performances between the two, but again, here the results are on a log scale. One can probably get a more intuitive idea looking at them on a regular scale. In the considered tests, we're up to 70 times faster than maximum likelihood. Furthermore, one point that needs to be put forward is that here we're testing our model with a batch size of 1, that is processing one alignment at a time, while the method is highly parallelizable and multiple alignments can be processed at the same time simply using larger batch sizes, the only limit being given by the available memory. Future work will include training the model on a more diverse dataset in terms of number of sequences and branch length distributions, which will allow us to beat maximum likelihood methods in a wider range, train the model on more complex models of evolution, which could be harder to deal with standard maximum likelihood methods, explore the performances of our network combined with different clustering algorithms other than neighbor joining, introduce a measure of uncertainty in the predictions, and further improve scalability. We wish to thank for their contribution Dexion Chen, Martin Raffo, Johanna Trost, and Philippe Weber. And thank you for your attention.